So Snowflake model is basically a customized model of star schema. A Snowflake model, as per the definition, a Snowflake schema is a term that describes star schema structure normalized. Every time you have a star schema, normalized star schema, that's called Snowflake model. What does normalized means? Through a outrigger table. So look at this model. One I have. This is a Snowflake model. So one of my dimension called store dimension is further normalized to store and region. I further normalized store dimension, further normalized to store and region, and therefore this becomes a Snowflake model. So if any one of the dimension is normalized further, that's called Snowflake model, and this is attached with some external dimension. So dimension hierarchy is broken into simple table. So we have a parent-child relationship. Now, when any one of the dimension is further normalized, in our example, the store dimension is normalized to store and region, and the relationship between parent and child. So region to store, in one country there are many store. This becomes a Snowflake model. Now what are the disadvantages of Snowflake model? Now in a Snowflake model, your query process becomes slower, right? You can compare this. For example, I'm writing one business query. We look at the cost of the query in both the model. So we'll write a query and I'm going to evaluate cost of the query. First case we'll look at the star schema, and second case we'll talk about Snowflake model, right? The cost of the query we are evaluating in terms of number of joins. The more join, the slower the query, because more comparison required. The basics, we stick to basic and fundamental of the query design. So my business query is, I like to find out, this is my star schema. First assume I'm writing a query in a star schema. I need to find out top 10 products sold in New York where store manager is John. There are many store managers. I like to find out top 10 products in last 2 quarters. So in order to answer this query, what dimension we need and what facts we need? First, we need data from period days. I need data from period days. So for last 2 quarters, data needed from period days. And I have a region called New York, or country New York, which is needed from coming from a country dimension. New York is from country dimension, right? Which is country dimension is region in our case. It is coming from region. And this is one dimension. So last 2 quarters where the store manager is John. So I've got a store manager John. Now this is coming from which table, which dimension? It is coming from, I've got only one table, store. Store is a normalized table, denormalized table for store and region. It's a one dimension. So stores, all this information coming from stores. For top 10 products, so product details, top products coming from my product dimension. So in order to write this query, how many joins you require? Number of joins. You can check. 1, 2, 3. Number of joins are 3. And a comparison become 3 comparison. Period days would compare to sales fact. When I join, period days will sales fact. one more thing I forgot. Top 5 products revenue or a sales. I need to find top 5 product based on revenue or a sales. So revenue and sales coming from my fact table sales fact, right? So number of joins. So how do you join? You join period days, join based on day key. First join would be with sales fact dot day key, right? This is first join. The second join with the store and sales fact based on store key. So you have a stores dot store key equals to sales fact dot store key. And third, we join with product based on product key. So product dot product key, so sales fact dot prod key. So this is my join. Number of joins are 3, right? So every time each row process, you compare your period days, stores, and product. When I normalize this table, store table I further normalize to store and region, right? Number of join increase to 4. So when it become snowflake model, number of joins become 4. And now in addition to these 3 join, you got one more join. And the 4th join become store key. So store is a region key, is a region key. Store dot region key equals to region dot region key. So you have one more join. The fundamental is that the snowflake model is good but not appropriate for your query processing. It is slow. The more join you have, the slower your query. In fact, we go back to the fundamental of database. As per the fundamental of database, when you from normalized model, the normalization, when you go to denormalized model, what you gain and what you lose. When you move from normalized model to denormalized model, in fact, what does it mean? Normalized model is your OLTP system. When you design your OLTP to OLAP, you can also call this, you have a highly snowflake model. From your snowflake model, you go to star schema. What you gain? First, higher query performance. The query process time would be higher. But what you lose, you have a lot of duplicate, a plenty of dupes. You have a lot of duplicates. And as a result of duplicates, if the more duplicates you have, the more space you need and higher maintenance. So we go back to fundamental of database. Why do you normalize? To manage your insert, update, and delete anomalies. And the overall idea have to normalize to reduce the duplicate so that you can lower the maintenance cost. And insert update operation could be managed easily. The normalized model is appropriate, well designed for transactional system and it is designed primarily for your insert, update and delete, whereas your denormalized model designed for select queries. So you see you have two different requirement and two different two different cause of using that. So whenever I use a star schema, I have a lot of duplicates, but on another hand, I can achieve higher query performance time. That's the bottom line. This is an example of star schema. Star schema is relatively easy to maintain and save storage space, and it represents the hierarchy in terms of dimension model. You can see hierarchy dimension model. What does it mean? My region become my parent, a store become my children. So you read this hierarchy would be something like this. You have region, you have territory, region, I think territory, region and country. You can look at the sample data to be very clear about it. So look at the region table. What's the hierarchy? Our region, territory and country. This is the order. This is my hierarchy. Region, territory and country. Under country you have cities and then you may have a store. So this kind of hierarchy is being built by looking but clubbing these two tables and become a star schema. So region is my parent table. In one country there are many stores. So cardinality you see 1 to many. Wherever it is pointing to 1 become a parent. Wherever it is pointing to many become a child. So in one country there are many stores. That's your snowflake model. From a Hyperion point of view, it is highly suggested or recommended to use the star schema. Star, as far as possible, try to go for a star schema. The star schema model is a recommended model. All for Hyperion as base data source, as Hyperion as base data source. So we prefer to have a star schema. So whenever we pull data from sources, we go back to the DBA team, data modeler team, and say, hey, it is good if you design this model, convert this model to a star schema. It is basically pretty simple. They can design a logical data modeling on top of that or physical data modeling. So when I do logical data modeling, they can rebuild this model. We call semantic model as well. So what data modeler will do, they design a logical data model on top of that. So I have data source. On top of data source, they create LDM. That's called logical data model. In a logical data model, what we do, we create a view. Logical, it's like a view. In simple word, my query would become like this. I would create a logical data model. Create view, view name, let's say view W. My dimension is store region. So we give a name called store and region. As we join these two tables into a single table. So for example, I pick some table from region dot territory, region dot country, blah blah blah, and store dot store name, I select most of them from different column from both the tables from store and region. and define a joining criteria where store dot region ID, they join based on region ID. This is what my DBA will do based on data model instruction. This is logic data modeling. Logic data modeling is a user view. It doesn't add any performance gain. Right? The difference between your views and a table. The logic data model just simplifies the user view, does not add any performance gain. Instead of logic data model, people can go for physical data modeling. So physical data model or logic data model, which one should be picked, depends upon various criteria. One of the major criteria is the space and administration cost. When you work in enterprise warehouse, for every changes in your enterprise or warehouse, any modification, any dimension, any tables to be added, it has to go through a long process. Most of the enterprise organization has a CAB called Change Advisory Board. If you change advisory board, evaluate, assess the cost of the query, cost of the data table. Is it really required? Is it mandatory? How much space it is adding to my enterprise warehouse, what is administration cost, maintenance cost, and everything. If they agree, we can create a physical data model. So my query would say, rather than we create a table view, I would use create table TBL underscore store region. So suggested is to convert this into physical data model if your enterprise warehouse permits you. If it is not permits, you can create a logical view. But suggested solution is to turn such model to a star schema. There are many instances when you don't have a star schema snowflake. You even have a more complicated model than this called a galaxy model. Galaxy model is like this, where I've got multiple fact tables. This is completely not accepted from HiPA implementation point of view. Galaxy model is pretty, it is not designed in such a way that I can use it directly. There are multiple ways to resolve it. So you see there are two fact tables. Representing two fact tables from a data modeling point of view, there may be two reasons. So Galaxy model, why do we use it? If you have multiple fact table, in our case, I've got fact table called sales fact and cost fact. Another one is cost fact. Why do we have two fact table? One reason could be they represent two different subject area. They're complete two different kind of analysis. One analysis pertaining to sales, another analysis pertaining to cost. So there may be two different subject area. The possibility one, we can convert Galaxy model to snowflake or star schema. You can convert this, but technically it's possible. You need to look at the business meaning to this. When you convert snowflake and Galaxy model to star snowflake, basically you are clubbing two different subject area to a single subject area, single logical unit. Does it bring any business meaning to you or not? Right? I assume when you convert these two add these two fact table to a single fact table, it's a meaningful. You are able to bring the meaningful data to your business. With this assumption, I'll tell you how do you convert this. So you have got two fact tables, right? Solution one, join two fact tables using confirm dimension. This could be one solution. Solution 2, split this model into two logical unit, and each unit is considered uh, as data mart, right? So what I do first, I apply solution first. Any dimension which comes between two fact table is called confirmed dimension. It is confirmed. So when you look at a simple logical meaning, each product has a sales detail associated. All the sales detail pertaining to the product stored in a sales table, right? Amount, sales unit, cost, other information. Each product cost detail, the unit cost of the product and other information, unit cost, unit price are stored into cost table, fact cost, right? So confirm product dimension joins to these two fact table, therefore it's a confirmed dimension. Every time I process data from these two fact table, the query would be processed via product. So in what I do, I would join these two fact table, keeping your product as a confirmed dimension. In simple word, I would, in first solution, we join fact cost dot prod id equals to dim products dot prod id, right? And first I join fact and dim product, fact cost dim product, and dim product with sales, fact sales. So next joining would be fact sales dot prod id, product id is a common key, equals to dim product dot prod id, right? A joins to B, A joins to B, and B joins to C. So A joins to C, right? This is what we do. A joins to C. That's exactly. So what I'm going to do, I'm going to merge these two fact table into a single fact table. I assuming, that's what I repeatedly say, I assume as per the business data it's a meaningful. When I process the query, I get the meaningful information by merging these two fact table. So my model becomes a star schema. By taking confirm dimension and join these two fact table. This is a recommended model for my high-pin implementation. Now, this is one way. Another solution is you don't merge these two fact table. Rather, you split this into two pieces, and each piece become one independent solution. So what do you do? You cut this, logically cut this piece. This become my one model. This become my one cube. And you cut another piece. This become your another cube. So there are become two edge base cube or two different model. One called sales analysis and another one called cost analysis. So one of these two method you can use. Data mart is this. Data mart is a subset of your enterprise warehouse, which is designed for a specific business need. It's a subject specific. So I can create two data marts, considering both requirements are completely independent. So one of these approach can be opted. So that's your all kind of schema: star, snowflake, and galaxy model. Now I've been talking about as base a cube or cube. How does a cube look like? I'll just show you graphically. So I was talking about multi-dimensional database. Multi-dimensional database, it's also called a cube. So this is your graphical presentation. I shown you in Excel sheet in Excel sheet, the cubes are displayed because we cannot display three-dimensional data. So what do you see over here in my Excel sheet? It's a three-dimensional data view, right? One dimension is your sales manager, province, and your time is a three-dimensional view. The same you see over here I display in a cubic fashion. It's a multi-dimensional view. One dimension is time, product, and region. And the small intersection you see over here is the data. In Excel, you can call this is your data. With the intersection of your time, province, and sales manager. Okay, now we use this often some term called sample data cube. You can have a subset of the cube, cut a slice of the cube which talk about one specific kind of analysis. So in this graphically, if you see one section, if you look at this part of it, this is quarter one sales, quarter two, quarter three. If you look at this part, this is called 4-quarter sales for TV. You can cut a subset of the cube and focus on a certain part of your database. That's called multidimensional. That's the beauty of your multidimensional database. Same thing, I have shown over here. I've got multidimensional database. I cut a subset of my one cube, and this is my subset. One subset. So I like to compare the sales growth by sales manager John and Mac. So one subset I cut from John, another subset I cut for Mac. Pieces, and so that comparison become easy, right? When you compare your data in these two cubes, this become easy. So that's called subset. Now we use certain operation on your cube. We talk about those operation, and then we further talk about other kind of hierarchy. So the operations are I think I've stored over here in Lee. Yeah, these are the typical OLAP operation. I show you everything live. Roll up or drill down, and slicing, dicing. I show you this thing live. Give me 1 minute. Okay, so you look at graphically, it is easy for you to understand. The first task is called roll up, drill up, or drill down. It's called summary view, and reverse is called detail view. So my hierarchy is like this. It's a year, time hierarchy, quarter, and month. Right? When you navigate your data from top to bottom, it means you navigate the year, from year to quarter, quarter to month. You're going top to bottom. So this is basically detail view. You navigate from, this is detail view. So it's a summary to detail view. Right? Now look at this. So this is my 1 year sales. How do you read this? 1 year sales. So this is a product for New York and actual. I go down. This is my quarterly sales. I can further go down, look at the monthly sales. So from year, quarter to month, I can go down and look at the summary to detail view. I can even go the other way around. I can do a drill up. This is my detail monthly sales. I can drill up quarterly sales. I can further drill up to yearly sales. So this operation is easy in your multidimensional database. Drill down and drill up. That's called drill down and drill up. Now what is slicing and dicing? Slice. Look at this graphical view of slice. A man is cutting a slice of a cube, right? What does that mean? I can focus on certain element of the certain subset of my cube. For example, I have a data for multiple province. I have a data for New York. I have a New York, Florida, and multiple province. But I like to focus only on New York and Florida. I can cut a slice of it. Though I have a data for all the province, I like to focus only New York and Florida. So I can cut a slice of it, subset of it, New York and Florida. I can even turn the layout, look and feel. This is called pivoting, pivot. New York and Florida, they were in rows. I convert to them to a column. Now for you, it thinks it's quite a silly thing. What's a big deal in it? What's the advantage? For the data analyst, this adds a great value. Look at this example. You like to compare month over month sales growth. I give you two views. As a business analyst, as a human being, you will easy to find when you organize your month over month in a column. It is easy to compare. Let's look at the two view. So month over month sales growth. Let's do on New York. So I like to compare January and February sales for simplicity. Month over month sales growth. You have got this view. Now comparing sales in rows is little uncomfortable. Rather, if you compare sales when you put them in a column, it is easy to understand. You know, human eyes feel comfortable when you compare objects from column to column. So when you convert your time from column to rows and rows to column, this is called pivot. Rotate your cube. You rotate your cube and identify some important business data patterns. So next operation is your pivoting, where you rotate your cube. Pivots. So we've seen how to navigate data in a summary to detail view, detail to summary view, rotate your cube, and focus on subset of the cube. That's all OLAP operation. Now these operations are pretty fast, and you see it happen with just a couple of mouse click. And behind the screen, the engine, every time I process my data, who process behind my processing of data, how it works. So from a relational database point of view, if I see my first query was, I was looking at yearly sales, right? Had I used the same thing relational database, it would be something like this: sum of sales, comma year, sum of sales, comma year, from, and group by. When you go down year to quarter, your query would be dynamically convert to, had I used a relational database, my query would have changed to year, quarter. Sorry, let me correct this. Group by year. And my query would change over here, group by year, comma, quarter. Then you further go down, yearly sales, quarterly sales, go down to monthly sales. Your relational database construct this query on the fly. Year, quarter, month. So moral of the story, the processing behind, if you use the relational database, the processing behind drill down and drill up is your RDBMS. So I would have RDBMS, and you have a presentation layer where you're processing your query, where you're navigating your output, data navigation. But query processing is done at RDBMS. Who process? Your RDBMS process this query. But when I use multidimensional database, I replace RDBMS with multidimensional database. So processing is done. The presentation would be same, but processing would be done by your multidimensional database. And multidimensional database is designed primarily for such kind of operation. So in fact, behind the multidimensional database, the data comes from some data source. It may be RDBMS as well. So it can be seen in this way as well. Previously, the data was processing through RDBMS. We add in between an additional layer multi-dimensional layer, and processing has been shifted from RDBMS to a multi-dimensional layer. This is what the benefit of adding multi-dimensional layer. The processing will be very fast. Right now we see a different kind of hierarchy. One kind of hierarchy, this is an example of a hierarchy. Typical, we have seen time dimension. It could be your geographical unit, it could be legal, it could be an entity, it could be reporting, it could be product, it could be custom specific, customer, different kind of hierarchy. We all talk about type of dimension. So far we discussed just a dimension. Dimensions are also certain type. For now we discuss a dimension called attribute dimension. So here I'm going to talk about attribute dimension and attribute hierarchy. Now let's take one scenario in order to understand attribute hierarchy. So attribute, as the name indicate, are characteristics or property of something. So I have a hierarchy of product hierarchy in my source, which a typical hierarchy says product details, product category, product line, family, category, name. This is my hierarchy. Now we see this hierarchy and look at, can we answer some of the business questions? Some of my business questions are, let me organize it well. I have got these questions. Let's check, is my model capable enough to answer this question? First, we need a list of the products based on consumer type. There are certain products are designed for different consumers. My consumer types are kids. Some products are designed for kids, primarily for kids. And some products are designed for gentlemen. Some products are designed for ladies. So you like to further categorize this product based on consumer type. Does this model answer consumer type query? Yes or no? No. The model, the hierarchy which I have, product hierarchy, does it answer this question? I mean, if I want to further analyze product based on consumer type, can we do this? No. Second question. It means we require, a model is not appropriate, it requires tuning. Second, we also like to analyze product based on manufacturing unit, where they were manufactured, or package type. The products are to be categorized based on package type. The products are available in different packages. Some products are available in bottle. They are further available 1 liter bottle, 5 liter bottle, something like this. And they are also available in can. 1 liter can, 300 ml can, 500 ml can, something like this. Now business want to analysis in which, this is a simple question, in which package type the sales is higher. A basic question, in which package type the sales is higher, so that the organization or a company should pay more attention to the package type and introduce more promotion policies. Wherever I have a low sales, the organization will introduce the promotion policies. But the model doesn't organize in a way that it can answer this question. So model, the hierarchy which I have, does not answer both of the question. It has to remodel. I need to remodel the hierarchy. So the clear answer to this question, there is a need remodel the hierarchy. Now if you look at carefully, these are properties. For example, this is my hierarchy. Let's take a product name. Assume the consumer type for this product name is gentleman. There's a primary design for men. Right? So I can attach certain attribute with this and I say this product is designed for men, this is designed for men, this is designed for ladies, something like this is designed for kids. So what do you see? I'm attaching an attribute. These are basically an attributes. They are characteristics. Package type, consumer type, they are kind of characteristics or properties I can attach with them. So what we do, I attach attribute to the dimension member. Or I could have also done the same thing. I can create a separate hierarchy like this. Consumer type as first is kids. These are the products designed for kids. This is an alternate approach. The same information would be stored more than one place. Another consumer type is ladies. And these products are designed for ladies. You see? So one hierarchy talk about this is a primary hierarchy. Second hierarchy could be a support hierarchy where we reorganize the product based on consumer types. This is a possible way. So I would do one way. I can attach an attribute with the members, or I can rebuild the hierarchy. In rebuilding hierarchy, you need to the same information you are storing multiple times. So naturally, you are occupying more storage space. If you talk about solution, there are two solutions. Which one you opt, it's up to you. Depends upon storage space or various other factor. This is called attribute hierarchy, which clearly tells you is self-explanatory. Attribute hierarchy. Right, so in a similar fashion, now the second question can be answered. The first question, list all the product based on the consumer type. I would like to see only those products which are designed for kids. So what I can do, I need to identify only those products which are designed for kids. So I can look at this hierarchy, or I can apply filter on my attribute dimension. This is called attribute called consumer type. And apply filter over here. I need only product for kids. Can apply filter. Right? We can focus, you see. So by adding an attribute dimension, I can apply filter and I can easily analyze the data. And you may have a sales. Assume you have a sales attached with this. You also have a sales attached with this. So you can further analyze your sales. So now your business question would be changed to, I need to see the sales detail only for consumer type goods, or kids or ladies. I like to compare. Consumer type kids. Total sales for consumer type kids. Total sales for consumer type ladies. So one clear advantage you can see by using an attribute dimension, the analysis become easy and you can add more attribute, more ways to analyze the same data. Same data can be analyzed multiple ways. Now the first question can be answered. Second question, we would like to further categorize the product based on package type. I don't have any way to do this. So I can add another attribute called package type. can add another attribute. So which product available in which bottle, which package, I can write a package type, bottle or a can. The same benefit you get over here. You can apply filter and analyze the product. I like to see only those products available in bottle. So multiple ways to analyze the same information by using attribute dimension. Another attribute dimension could be package type. And this is my hierarchy. So the core data comes from your source system, may not be smart enough or may not be complete. On top of this, your business like to do analysis. There may be a further need to remodel it, add more attributes and characteristics so that you give the higher degree of analysis to your business user. But you see the driving force is your requirement. I've taken two requirements and based on this, you analyze a model. So that is what your attribute dimension is, an attribute dimension hierarchy. So all the important building blocks we discussed today. One more point we'll continue to discuss tomorrow. Where does, in a complete enterprise warehouse model, where does high-end products fit into picture? This is what we are going to discuss in tomorrow's session.